Testing 1, 2. Thank you, sir. All right, guys, so good morning. So we just have about 45 minutes? I think about 40 minutes. So I'll just do an example, maybe one or two, just to finish what we've started. So last time we met, we talked about groundwater. I think we spoke of the different types of aquifers that are there. We defined what an aquifer was. We defined what an aquitard was. We are talking. Okay. We talked about, what else did we talk about? Some definitions that you can still remember. Yeah? What do you remember? A what? I can always get a hand. Yes, sir. Could it be? Okay, it's okay. It's okay. Confined aquifers. What is one major difference between a confined aquifer and one that is unconfined? What do you remember? Major differences that you can remember? Okay. So where we left off, we had two formulas, right? Is it formulae? And these were pertaining to the confined aquifers and that one which is not confined. And so the major of this topic is someone just asking you questions like how much water is going to come out of this strata given the parameters. So questions will be given, then it's up to you to determine whether that is a confined aquifer or unconfined aquifer. The question may state, sometimes it may not state. It's all dependent on how much information you have. So, the last time we met, I also mentioned that the formulas that we have, the next time we meet, we're going to have an illustration, a sketch, to sort of define what the parameters were. Are we together? Okay, so let's just continue from where we left off with this sketch so that we know what RW is, HW is, what the D is, and everything that we need. So imagine you have a ground surface that looks like that. And then you've got your piezometric head or the water table. You've got an impermeable layer, which can also be known as an what? An aquitard, right? So, we have drilled a borehole through. All right. I hope this is legible enough on the camera. So we have drilled a borehole, and what we have here, this is an aquitard or an aquiclude. Who's ever come across an aquiclude? And what is it? It's just another name. You sure? All right, so let's have the sketch so that we can define the parameters that we saw in the formulas that we gave yesterday. So we can say this is an impermeable layer. Okay, so this and this are particularly just the same. And then we have our confined aquifer here. Okay, so if we're being more specific, we're just talking about a confined aquifer here. And we're trying to find the parameters that were in the equation and how they sit here. So this is your borehole that you've drilled through. What you're extracting out is our Q, and we saw that from the equation. The depth of your aquifer is the one that sits here, and it's denoted just as a capital D. The height to which water in a well after pumping maybe for a day gets to is what we refer to as HW. So from the base of an aquifer to the levels of water in that well, this value is of interest to us, and it's denoted as H subscript W. Then we also had a denotation of an RW. So RW is just the radius of the well. So the well will always be given a diameter. Wells, you always be asked how big do you want your well to be. Okay? So if you're given a diameter, you know how to use your RW. Just get your radius there. Then the other value that is very important to us, and someone asked about this yesterday, okay, it's just the R1. This is also known as the radius of influence. Okay, so R1, so we can just say radius of influence. Okay, and the radius of influence is just the distance that you get from the middle point or from the center of your, come on. Am I in the frame? Like sawa na che guys, sawa na che. Akodeo? I'm in the frame? Okay, cool. So R1 is just the radius of influence, and the science behind this is where you've drilled the borehole, okay, and you start abstracting water. The effects go, so view it from the top, right? So this is your borehole from the plan. Your influence is circular, okay? So you can't just affect the water table in one direction. If in one direction you've moved about 10 meters, and I'm going to explain what I mean by affecting the water table, it means that every equidistant or every distance away from that borehole is affected in the same way. That's why it's called the radius. So a radius is a radius of a diameter, right? So it's the radius of influence. And what they mean by that is this. Initially, before you start pumping, this is your water table. Are we together? Are we together?
Yes, sir.
When you begin pumping, your water table changes from just being a normal line to coming to this level. So it will look something like this. So either I can leave, let me just leave it like that. So initially, before you pump, your water table is maintained, right? When you begin to pump, the water levels here begin to drop. As they begin to drop, they drag this line along with it. So this is where you're having these lines that look like that. So this one is just showing the original water table. And then, of course, with time and with pumping, the water table just sort of drops. And if it is dropping, it is dragging along that line. And the radius of influence is always from the centroid of your borehole to where your curving just starts to touch the water table. So where the water table is still original, that's how far your borehole is affecting people. Does that make sense? Yes. So let me start from here. If this is your borehole and you start getting out water, your water levels as a water table begins to drop. Do we agree on that point? Look, if we're not agreeing on that part, then there's no need of continuing. Do we agree? Yes, sir.
Maybe why I'm not getting it personally is we're not drawing water from the water table, not. So our borehole is dug in our aquifer. So why is it that the water table is dropping as we draw water out of our aquifer?
That's a very good question. Why are we drawing the water from the water table? Yes, sir.
So the reason why the water people are treating from the water table is the more we pump out water, the more water people reduce it from the aquifer. Now the reason why Sianga see Masasa here today because the layer of the aquifer is permeable. It allows more water from other sources to pour into that aquifer.
The definitions that we gave yesterday, we did not say absolutely that this can't get depleted because you're not the only one who's drilled through. So it will still reduce. And whenever you pump when you punch through your aquifer, water will rise to a level of the water table. That's the science. But depending on the pressure, like we said, this could actually go even beyond to a point where it's gushing out. But the worst case scenario, in a confined aquifer, when you punch through the confined aquifer, water will begin to rise and it will get to the water table of that very stratum. So that's the science behind that. Of course, it won't drop as fast as the unconfined. It makes sense, right? Yes. Exactly. Why? Because this guy is a little bit protected. He's under some pressure, and we always have water coming from all directions. Because when you drill a borehole, what you do is that you drop your pump, and it just come and sit somewhere there. All right? And then, of course, this pump will come with its own electrical cables and the pipes. When you run the pump, this guy draws water from all directions in a circular or radial manner. So it's pulling the water. But originally, the moment you just pump, this aquifer releases water to the water table of that soil. Okay? So for academic purposes, we're just going to imagine that the water levels are just reaching the water table. So let me just say water table. So when we start pumping, these examples are usually put in a way that when you pump after 24 hours, you come and take a measurement. So when you pump, what happens to the levels? They begin to drop. The levels to which this won't drop is to go beyond or below the water, the aquifer, the confined aquifer. Then that won't work. The only protection a confined aquifer has, you can never see water levels dropping below its depth. It will always maintain this value. Okay? So if this is the original value that you found by depth or height, when you start pumping out water, it begins to drop. And when it's dropping, you expect that the line also curves down like that. Nan saramvere manja. So the radius of influence is in a sense that what's happening on my right-hand side is equally happening on the other side. So this distance should be the same as that distance. And the radius of influence is only to a point where your water table is just about to curve because it hasn't been affected. So this borehole has been affected from the middle parts to just where it's about to curve in. As long as it hasn't curved in, then we say that your borehole hasn't affected the neighbor. And this is very important because we want to know, you as Mr. Maybe Banda, you drew a borehole. No, Mr. Mwale, thank you for that. We want to know how far your borehole is going to affect the next person. Because the next person, again, they'll drew a borehole, it's also going to have its own radius of influence. So, there's a point I wanted to say here. Exactly. So, how we know where the radius of influence is we have what we call just test wells or observation wells. So it could be just a well, something very small, very simple, that allows us to measure where this is ending. Observational. Okay? From our formula, this distance is very important. From the bottom part of your aquifer to where your water table just begins to curve. And this is what we're calling, what value was given here? H what? What other particular is missing from there? H1, right? Yeah. So get this, it's very simple. Everything and anything related to the well itself, it's got height of the well, the radius of the well. Are we together? But anything that is pertaining to the observation well or the radius of influence, we have R1, and this always moves with H1. So when you're given a question, I think this is all. What else is missing? Yeah, chap. Those are the major ones. So this is the ground surface, of course. Yeah. For an unconfined aquifer, it's basic, okay? It's basic. We have your surface, you have your water table, and then you maybe just have your base where your water is. And what you're going to have, obviously, is your borehole being drilled there. And what's of interest is that this guy can also equally curve, okay? And so we are still calling this guy RW to the depth or the distance it's affecting the neighbors, it's still R1, and the height equally here is H1, right? The height to which we are moving water in a well is still called HW. And then, of course, whatever we're pumping out needs to be known in volumes with the units that we know discharge to be. Chapa. So this is your ground surface, and this is your water table. So when you start pumping, this is to the levels water will drop. And then maybe this can be an impermeable layer. So just so that we show the main difference. So let's say aquitard. So that's it. And wherever we're measuring from, this guy is also known as an observation well. Observation well. We're observing just how far our neighbor is drilling or is abstracting water. Okay? So those are the major differences. So whenever you begin to solve these questions, what you want to always do is understand these parameters. How do I get my RW? How do I get my HW, my H1, my R1? What is my volume? And then what are they asking me to find? Usually you'll be asked to find the one value, which is the permeability of the aquifer. And it's denoted by the value K. In our equation, we had the K, not so. That value is sometimes known as the permeability of the aquifer. It can also be known as the coefficient of permeability. It can also be known as, exactly, hydraulic conductivity. So basically your K just informs you of how fast this medium you're drawing water from is allowing water to pass through it. Are we together? When we were defining what an aquifer was, apart from it being under the surface, we said it needs to give you enough water that can be useful, not so. So when we are calculating, we're trying to determine the value of K if it's within the range that it allows water to be abstracted at a good rate. That's why it's important for us to find the value of K. It tells us of the value of the medium. It tells us of the quality. One, does it hold water enough? But then two, does it allow enough water to be abstracted from it? Okay? Okay, this one is a long question. Okay, let's do one question. The other one we will solve on our own eye. Kind of so mature. Okay, so problem number one, or just exercise one, or example one. Water is being pumped from a borehole driven into a confined aquifer. Water is being pumped from a borehole driven into a confined aquifer. Water is being pumped from a borehole that is driven into a confined aquifer. So sometimes the question will be so clear or easy that they will actually state that this is a confined aquifer. Sometimes it won't. But really the major difference is the moment they mention the depth of the aquifer, then water is being pumped from a borehole driven into a confined aquifer, full stop. The pumping rate is increased slightly day by day. The pumping rate is increased daily. The pumping rate is increased slightly. The pumping rate is increased slightly day by day. The pumping rate is increased slightly day by day. Until the static water level, until the static water level in an observation well, in an observation well in an observation well 180 meters away, 180 meters away, 180 meters away, just starts to fall. Just starts to fall. Just starts to fall. Just starts to fall. Full stop. Estimate the aquifer permeability. 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 Full stop. So after that, so just come and write data. So this is just like information or data, additional data concerning the borehole in question. So after you write data, say aquifer thickness 49 meters radius. Aquifer thickness 49 meters. Aquifer thickness 49 meters. Radius of the borehole is 0.3 meters. Radius of the borehole is 0.3 meters. Full stop. Maximum rate is 10 liters per second. Maximum rate is 10 liters per second. Maximum rate is 10 liters per second, comma. Height of original water level, height of original water level above top of aquifer, height of original water level above top of aquifer, full colony. Height of original water level above top of aquifer, full colony, 30 meters, comma. Height of water level in the borehole, height of water level in the borehole, height of water level in the borehole, open bracket, at maximum pumping rate, at maximum pumping rate, close the bracket, at maximum pumping rate, close the bracket, above top of aquifer, full colony 12 meters. Full colony 12 meters. Are we there? So above top of aquifer, 12 meters. So I said open bracket at maximum pumping rate, you close the bracket, then above top of aquifer, 12 meters. We okay? So that's almost like from, depending on your handwriting, it's like half a page, right? So just instructions. And usually in engineering, it's a lot more like that. You'll be the contractor, the supervising engineer, will give you documents. This is a road, this is a building. We want it to look like this. This is the strength of the steels, the columns, the beams, the floor. I didn't want to say floor. The best, whatever. So you deduce that and make it from the instructions. So they'll give you something as this. This is a borehole. It's got so much of parameters. So from this, I always tell students, please have a sketch when you're solving this kind of equation. You may make a mistake somewhere, but if you show me that every value there is sitting where it's supposed to sit, then it makes sense to me that you understood and maybe just made a mistake. So always have a sketch also for your easier calculations. So 1, the discharge was given as what? And I want to be putting them here. Okay, so we can say discharge is equal to a 10 liter per second. The units, we are working with the SI units. Distance should always be a meter. Time should always be a second. I think basically that's just what's there. So meaning your volume can't be in liters. You convert this into a cubic meter. Are we together? All right, so we'll have 1,000 liters giving you a cube, but then the second is okay. Punching. What's that value? 0. What? 0.01 cubic meters per second. So you get that value, convert it in the right units, and then you just plug it here. This is where it belongs. 0.01 cubic meters per second. They gave us the depth of the aquifer. By the way, this is a confined aquifer, right? This is why we're working on this diagram. If it was unconfined, I would have deleted this and worked on the other one. So pay attention to which one you're working with. The depth of the aquifer was given as 49 meters. Then they gave us the borehole radius, which is your RW, 0.3, right? Okay. What else was given? The height of original water level above top of the aquifer. So top of aquifer going to the original water table. So we're talking about this value. Yeah, let me talk about this first before I write. Yes, this is an aquiclude. Yes, this is impermeable. Are we together? But for calculation purposes, we do not consider the depth of this material. Tomfwana. So when they say the top of an aquifer, you can place your value from here to go there or from down here to go there. It doesn't matter, as long as you're consistent with your baseline. So this depth doesn't matter, okay? So it's negligible. So the value given here, I'll try to use just the top of it. What value was given? 30 meters, right? And then they also say the height of water level in the borehole at maximum pumping rate above top of aquifer is 12 meters. Meaning, and let me have your attention, if you decide to make the top, and this is after the aquiclude as your baseline, then you need to remain consistent even when you come here. So your 12 meters will come and sit here. But if you're using the lower part of the aquiclude, which is the actual confined top base, to draw your sketch, it means that even here it will need to start from here. You design it that way. But just to make your work a bit more neat, I prefer using just the top of it. So we have our information there, and then it's just a matter of, no, we're not yet done. They say the observation well is 180 meters away from the pumping well, not so. Meaning, and I mentioned something about the observation well, meaning your R1 is 180 meters. And so the question said, the observation well is 180 meters away just when the water table is about to fall. Okay, so I think I talked about this. So this is the original line for the water table. Just when it begins to fall, this is where you mark this value. So meaning you already know what distance this value is if it's down here to there. Do we? So in short, what will be your H1? What's your H1? What's your H1? 79. How are we getting the 79? Plus are we okay? So it always takes you back to what is the sketch, how do you get your H1, your HW, and all that. So if they say that 180 meters water just about to fall, meaning we're still covered, we're just there at that point where it's about to fall, meaning the distance from the water table to the aquifer still remains the same. But you know that from the formula you need your H1, and your H1 always starts from the base of your aquifer to where the water table is. So we need to consider the whole lot of this. What will be your HW? How do we get in the 61? Are we together? So once you do that, the rest is basic. Okay, so once you have these values, I don't need to put them here, I already have them. So I can say, therefore, our K, which is the permeability factor that they're looking for, is equal to a Q, lean open bracket, R1 RW divided by a 2 pi diameter, or D, H1 minus HW. So we've got a 0.01, lean open bracket, R1 is 180 over 0.3. We're dividing everything by a 2, pi 49, open bracket, so it could be a 79 minus, we say 61? What are the units for the values of K? Distance per liter, right? Who's got the confidence to just punch this value? And I would urge you to know how to work with, especially the lean here. It always messes people up. So know your calculator, which one is the lean, so that you get the right answer out. Someone to punch that? Wangu wangu. If I can get the same answer from 2 or 3 people, I think it will be okay. Let's go. We only have 2 minutes. What are we getting? You guys are good with math, so we might as well just leave it here and assume that we know what we are doing, right? So, an additional question that comes from a question such as this one is transmissivity. I was trying to look for where they wrote something about it in the module. What is transmissivity and how can we go about it? I saw you somewhere. Okay, so there's a component that is of interest to us whenever we calculate this. It's known as transmissivity. So just write something before we get to that value. So just say transmissivity. Transmissivity. So I'll dictate, it's just 1 or 2 sentences. The transmissivity. Someone's was spelling. TRANSMSIVT. TRANSMISSVITY. Transmissivity. Transmissivity. So let's write something about it. The transmissivity, comma, put capital T, another comma. The transmissivity, comma, put a capital K, sorry, T, because that's the denotation. After the T, after the capital T, you put another comma. Of an aquifer is a measure of how much water can be transmitted horizontally comma, such as to a pumping well. Such as to a pumping well. Such as to a pumping well. So I said the transmissivity, capital T, of an aquifer is a measure of how much water can be transmitted horizontally, comma, such as to a pumping well. And this is how you find it. So it's just a T is equal to K. And the K is the one that you're finding here. Are we together? So it's one of those questions, if you screw up on the first one, then even the second one you might as well just, and then the D. Okay, so the hydraulic gradient or the permeability of the aquifer, you're multiplying this by the depth. So the depth, you already have it in the question. What else did I want to say? Okay, I wanted to explain what this is. So they're just talking about the rate at which this aquifer is able to transmit water horizontally. So I say that if you put your pump here and you run it, water begins to gush or to run to where it's being caught. Not so. So the rate at which water is moving when you switch on a pump, that's the transmissivity. It's just a horizontal movement of water. But then you find that the units, because this guy has got units of what? Meters per second, it's literally speed, right? If you're going to multiply by the depth, what's the value for depth? It's just a meter. So your transmissivity by units should be an area over. So from an area, this piece of an area, its distance or its area that is moved per second. Okay, so that's that value, and probably I don't even need to solve this because we already have the values. So one additional information to this, just write this. Transmissivity is directly proportional. Transmissivity is directly proportional to the aquifer thickness. To the aquifer thickness. Transmissivity is directly proportional to the aquifer thickness. So this means that the bigger the aquifer depth or thickness, the bigger the transmissivity, not so. Okay, so Chapwa. So this is an example of a confined aquifer. So just understand how you get your H1, your RW and everything. But what I want you to go and try is the extreme that you would expect when it comes to this topic. If you understand the concepts, it shouldn't be that hard for you to find the answer or the solution. So in your module, on page, who's yawning? On page 92, there's problem number 1 there. Page 92, problem number 1. I skipped it. I'm not in the mood to solving hard stuff right now. So I've left it to exactly the geniuses with the energy and the task to prove to me that they've understood this course. So give it a try. It's got, the principle is just the same. All right. Okay. Any questions as to where we are now? So we'll see you. Oh, yes, sir.
The question I have is on confining beds.
Yeah.
Confining beds, can they either be made up of an aqueduct or an aqueduct between the two? Which one is mostly confined bed?
Both actually work. They just differ in the material it's made out of which this course hasn't really gotten deep into them, but it was supposed to sort of give us the properties of an aquiclude and an aquitard. But they just fall in the same bracket. They don't give out water at the rate at which you'd want to use it. Yeah. Any other question? I saw a different hand. Yes, sir. What's that? Transmissivity. Practice that, sir. You need that word so that when you go and see client, you are explaining to them such ways they'll be like, oh, you need engineers or now. Because they can't explain it or pronounce it the way you are as well.
Now, the definition that you gave, now what if I define it this way? The rate at which water flows through an aquifer, is it okay or?
Yeah, no, it's fine. It's still great, yeah. We're just trying to find out how water is, how fast.
Yes, I just want to get the distinction between the cone of compression, this one, and also the drawdown maybe in the well.
Yeah.
The drawdown of water, as well as extracting water, and also as we are drilling the cone of depression when we are drilling through the.
Sir, let me have your cable, that one. Yes, bring it. I'm being practical now, aye. Idea we should be having a lab. Buera amene. Buera. So come and hold this just from there. So imagine this is your water table, right? And then somewhere here you've drilled through a borehole. And this borehole is dependent on how much water you're having. When you start drilling, the water level begins to drop. Are you seeing what's happening in the water table?
It's forming the shape.
Yes. But not just on my end, on his end as well. Even on this end, even on this end, even on... I hope this is a cable yakwa. Does that make sense? So this is the cone of depression. So this is the cone. Ideally, then it... So the deeper you pump water out, the more it goes even further. So now this is us imagining that if we maintain our positions in his, where my hand is, this is where the observation well is. Where it's just about to start dipping, but when you start pumping from here, it's... But then imagine it being circular. So this is... Okay, thank you, sir. This is what's happening here. So originally it's here before you pump, but as you pump day by day, slightly, steadily, it begins to drop. But then it can't just make a sudden drop here and maintain the line here. That is not realistic. So when it begins to drop, because it's one line, it drags along with it the other sides of the soils.
So again, the other one.
Hey, he's got questions, man. Yes, sir.
Yeah, it's my question. I'm just checking with myself. Because not only that it benefit me, it does benefit all of us, I'm sure. So maybe in terms of the water that is in the void spaces, we are being told that the drawdown. So I wanted to differentiate really know the distinction between the cone of depression and the drawdown in the void space. Because when we are starting water, that drawdown of water is created. So I'm trying to appreciate. I remember asking.
Yeah, well, but you understand about the cone of depression, right? This depth here, this is what we call the drawdown. This was the original position. Then it has dropped down. So this is your drawdown. And it's asking a very valid question because the question that I've given you is asking you to find the drawdown, right?
Yes, sir.
It's asking you to find how much we have dropped. And you need to do some math. So understand the formula and where can you get that drawdown. So there will be a need for you to make a certain value which isn't originally. What's that term again? Yeah, a value which isn't originally. What's this? No. Like in a mathematical equation, what's this? The subject of the formula. Nambokota. A bunch. Yes, sir.
Like when you're making each schema,
Yeah. Yes, sir.
That's a water table. What? Because as you are going down, example is mines which is mixed with soil. Then you're supposed to be moving the water out until you find just the clear water down.
Yeah.
So that is the liquid water. Is it the water table or what?
Yeah, definitely, it's a water table. I mean, if it's like you said, Chishima, those are like hand dug wells. I know you can't go as far as drilling through the aquifer. So it's just a water table. And you find that the more you draw water, for instance, it's also dropping. Maybe as seasons go, as the season goes. Yeah, so it's a water table that you've, yeah. Okay, yes sir.
Simply meaning the first layer of permanence, the first layer of the water table.
Yes, yes, it's a water table. It's a water table. That's why it's very worrying from a sanitation point of view. You find your water here, and it's very close to the ground. It's a hand dug well, like in Maploti, because I've lived there before. And then just barely 5 meters away, there's a pit latrine. And this pit latrine as well actually has its troubles of water that are also interfering here. And as long as your water table is running there, it means the waters that are here are able to run back and forth. And they are in association. The only reason why you may not experience problems just there and then is like a bit of distance, and then water finds time to move through. Bacteria are unable to filter through the media. But then the closer it is, that's why we always discourage that. The closer the toilet or the pit latrine and your well are, the easier the bacteria can survive through the soils. So we try by all means. I think we've given a 30-meter apart. Okay, kwasira manje. All right, guys, so we'll see you next week, hopefully.